Okay, so this series of videos is going to be more about the internals of Predbat, how the code works. This isn't designed for a user, this is designed for people who are either developing on the system further or just want to learn about Python or other developments by looking at an existing application. So today I'm just going to walk you through the files and the basic framework. And then in subsequent episodes, we'll move into details about each of the different parts of the code itself. So what I've pulled up here in my Visual Studio Code is the actual application folder from Home Assistant that contains the code and all the files that are present here. So what you'll notice is a number of directories, and most of the files are actually in the main add-ons directory. So if you open this folder in VS Code, you can get to edit the live code here. So a few things to note. So Predbat.py is the main sort of application code, but it's not actually the entry point, because if you're running an add-on, then there's actually the Home Assistant add-on first, and that actually has some code that will not be visible in here. So it has its own add-on startup framework, which actually, if there isn't any code here, will actually go and download the latest version the first time and then store it into this add-ons directory here, and then it will stay there for subsequent updates. The first thing it then calls is this thing called has. So has is essentially the standalone version of Predbat. So this only comes with the add-on. If you were using the older AppDaemon, then AppDaemon would be doing this. So this is kind of like my wrapper for that. And so what you'll see is a main here that runs. And if you look, there's a few other functions in here as well. But essentially, there's some code here that when you execute this has, it essentially calls using async IO to run main and then exits. So that's like the main entry point if you execute this, and that's what's run through the add-on. And then if you look at main itself, it prints this message starting standalone Predbat. And then it actually constructs the application. This is the class Predbat that's in this file. And then it calls the initialize method in that class. And if anything, if this fails, then obviously you get an error. And then what it does is it finds all the files in here that are Python or all the apps.yaml file. It adds them to a watch list, and then it goes around here and it sleeps, and then it essentially calls the timer tick handler, and then it checks if the files have been modified, and if they have, it actually calls the stop method that cleans it up and then finishes, and that will cause this to exit, and then the add-on will exit. And then when the add-on starts again, it will start with the new Python code that's modified. So if you edit one of these Python files, it's going to restart Predbat automatically, or if indeed you edit your apps.yaml. So that's kind of how the thing works. And this timer tick here, if you look at it, doesn't do anything very exciting. It essentially looks at the run list and it sees what on the run list needs to be run next, based on the timing. So it's essentially comparing each of these items, and this run list is created when you call the initialize application. It will queue things up that need to be run regularly. And so this run list is looking at the current time, and if it's past the next time that it's due to be run, then it calls that function. And if it fails, it prints a trace. And then after that, it increments the next time that it's due to run. And in fact, this is slightly different from AppDaemon in that if you miss one of them, then it will call it. It won't call it again. It will just skip the next iteration of it. So what happened in AppDaemon is if you were updating the plan every 5 minutes and it took 6 minutes to update, you'd end up with an infinite number of threads scheduled and eventually it'd crash. Whereas here, if it took 6 minutes to update, it will skip update on number 5, and it will just pass it by and end up updating again at minute 10. So I think that's a bit more effective way of doing it. So some callbacks in this code as well. So when Predbat calls the callback run every, it essentially adds it to this run list, which is being scheduled here. And it just adds the information as to when it's next due to run and how often the frequency is. And there's essentially an init function here. And the init function, which was called just once at the beginning, is the thing that opens the Predbat log file. And it also reads the apps.yaml. So it saves the log file handle, it reads in the apps.yaml, and it saves that as well. And if there's an error, it throws it. So then there's some other handling around here. So this is all in this Has class. So this Has class itself has got a logger method that essentially writes to the log file and rotates the log files when they get full. And it's got some little Python tricks here to do with creating a task. So creating a task actually creates a new thread and then schedules that thread here. And then there's something that waits on the thread for it to clean up. I won't go into detail on that, but it's some little Python tricks, and the stop all essentially calls the terminate for Predbat, and it closes the log files after the threads are finished. And this is a join timeout, so it's 5 minutes. If the thread still haven't finished, this will just exit anyway. So that's really it for the wrapper. So the Has class, you could think about it like an app daemon replacement, essentially. And that's the way it works. And what you'll find is that Predbat actually inherits this Has class. Sorry, I forgot to say that. So this is the functions that Predbat calls, as if in the old days it would have been app daemon, but these are its own functions. So when you see self.log in Predbat, it's actually calling this log method. When you see self.runExecutor, it's calling this one, and so on. And so this class Has is inherited. And so when you go into Predbat itself, you will actually see the main class Predbat here inherits this Has. And Has.Has is essentially, it's called that because that was what it was called in app daemon. So essentially, if app daemon is present, it uses the app daemon one. If not, it uses my one of it. So eventually app daemon will get retired, but at the moment I'm supporting both of them. Right. So that's how it all gets started, and the threads get scheduled and it kills as well. So looking at this main Predbat file, what you'll see here is there's a bunch of imports from certain libraries. Nothing very unusual about that. You'll see a file list here, and this file list is used for the downloader function to know what files to download. More about that in that section. And this is the actual downloader itself that's imported. And then there's this check install function, which essentially gets called whenever Predbat starts, because you can see this is essentially global. So when you import it, it's going to call it. And check install actually is a function in the downloader code that checks that all the files that are meant to be present here are, and if not, it says all your installation's corrupted, and it automatically schedules the download again. And if it is installed okay, it just says installed okay for this version. The version number here is important because that's compared against the version on GitHub. And so prints in the status of Predbat what the version is. Config is something that contains a bunch of global information like these configuration items, and also the config items table. And then it imports some of the other classes here. So obviously config is going to be config.py, which you'll see here. And prediction will be prediction.py and so on. So this prediction is essentially the model which models the your actual system, essentially the inverter and the battery, and so you can set it up and it will make predictions. Utils is just a few utilities that are used by various bits of code. Inverter is the inverter control logic that supports multiple inverters. It's the thing you call things like set a charge or set a discharge on. HA is the interface to Home Assistant. This is how it talks to Home Assistant. and communicates, writes entities, reads data from it. Web is the web interface. Predheat is actually the Predheat model if you're using that. There's models things like heat pumps, and future rate is the future rate model for like Nord Pool, etc. In the future, I'm going to add some more files and split some more of this code up into classes, but I haven't gotten that far yet. So what happens when we start Predbat then? So the initialize function, which is inside the Predbat class, is the one that was called from that Has, and this actually does the initial setup. So what happens here is there is update time function just fetches the current time and date and that sort of thing, and then here we initially the first time we perform a reset that just resets a lot of the class variables, and then we construct the Home Assistant interface, which essentially is the thing that opens a communication line to Home Assistant through WebSockets, and obviously does the authentication, that sort of thing. Then we start the web interface, which actually opens the HTTP server that you can connect to. And so the web interface itself has got a class, and then it is a task that actually runs because it runs in parallel in the background, obviously. Then there's a bit of information here where it's looking for the name of this add-ons directory and storing it and then printing it out. There's some sanity checks which really were based on AppDaemon to check you configured it properly. I don't think they do very much in this standalone one now. Home interface and update states is like the first run where it queries Home Assistant and gets all the state information for all the states that we're tracking. And then auto config actually loads the current Predbat dynamic config. That's the things that are configured inside Home Assistant. So if we have a look at that, so actually what this is doing, sorry, I'm wrong about that. Autoconfig is the thing that looks at the apps.yaml regular expressions and matches them up against sensors inside Home Assistant. Load user config is the thing that loads the actual configuration items based on these config items here. So this is all a bunch of setup. Then this is just some errors if you've got a template config. And then essentially it calls these run every functions, which we saw inside Has, that then puts these tasks on a queue to be run every so often. So it's basically every 5 minutes, every 15 seconds. And then also, if we've got balance inverters enabled, it schedules that balance inverters to run frequently as well. I think again that's however many seconds that is running, say every 60. And if we've got Predheat, it also constructs that application, initializes it, and that initialize will also call the run every and get itself running. So that's scheduled all the tasks, and then terminate when it's called. This is when we shut down. Essentially just tries to clean things up, so it stops the web interface. It's by setting a stop thread variable, the web interface will notice an exit. And also if we've got a multiprocessor pool, it tries to terminate the pool first and then quits. And then we have the functions that are called regularly, and there's two versions of those. So essentially we have update time loop, and we which is the one that's called every 15 seconds. And this essentially triggers if there's an update pending, which essentially means you've toggled something in Home Assistant, it'll set that update pending, and it means you need to recalculate now rather than waiting for the next 5 minutes. And essentially what it does is it notes that it started a prediction. That's just to stop multiple of these going at one go. So if this calls again for another toggle, it will just skip it because you've already started a prediction. It updates the states from Home Assistant. It re-scans the user configuration items to make sure to see if they've changed at all, which they're likely to have done. And then it actually updates the prediction. Create entity list is essentially something that writes out a file of entities, and then it records the status. Oh no, sorry, this is only if there's an error. The status would have been recorded inside update prediction. And then runtime loop is basically the same, but this is the one that's called every 5 minutes. So the only real difference here is it only reloads the user config if there's an update pending. I'm not sure why I haven't merged the code for these two together. It may be possible just to have one function. Anyway, it is as it is. Runtime loop balance is essentially the one that's used for balance inverters, and that runs every, say, 60 seconds. It's completely separate and just calls the balance inverters. But if there's a prediction started, then it'll skip, because otherwise they're going to fight each other. So that's the main loop here. We can see this check entity refresh is also the so this is the thing where it's essentially check if we need to refresh configuration entities in Home Assistant. So this essentially updates state from Predbat and pushes it back into Home Assistant. And sometimes this needs to run because they get too old. So in Home Assistant, the way that the data is recorded for Predbat, because it's doesn't have an entity ID, they're kind of transient. So if you reboot Home Assistant, or the values get older than a certain amount and haven't been refreshed, Home Assistant throws them away. So here it actually checks how long it is since it's last refreshed them based on this entity, and then if it has waited that long, then essentially it will trigger an update pending here, and the update pending will cause it to do the refresh. This also calls the DB tick in my Home Assistant interface, and that is the thing that commits data to the standalone database. If you've got that enabled, that feature's kind of something I've been beta testing at the moment, where Predbat creates its own SQL database, SQLite, and it stores all the state information in there, as well as a Home Assistant if you're using it, and then you can query that directly, and it can make the queries faster and things, but I haven't rolled that one out yet. So that's the main framework, and then obviously the actual prediction itself is this update prediction function, which does most of the work. And if we look at update prediction, then we'll see the different steps that it goes through. So update time is just updating the time information, and then save current config essentially saves the current user configuration to a file if it's changed. And then it marks the active sensor as true, saying Predbat's active. Here is the thing that checks if there's any new releases to download from GitHub and flags that. Then it fetches all the configuration options. And if you look at fetch configuration options, then this is all the options that we get from, say, the apps.yaml, for example, or from the Home Assistant configuration. You'll notice the difference. The ones in apps.yaml don't have a default, essentially. Sorry, the ones that actually do have a default, like this one, forecast hours, whereas the ones that in Home Assistant don't have a default here because they're described in the defaults table. And so it stores all of those as class variables. So if you wanted to add new config options, you need to add them to config.py, and you need to add them here to store them, essentially. And then fetch sensor data essentially fetches the sort of the data that's got history from Home Assistant that we need to store. And so that'll fetch things like your energy use history, or indeed from Give Energy Cloud if you needed to. It would fetch the Octopus energy rates, gas and electricity, depending on how it's configured. It would fetch the Octopus intelligence slot information, car charging times, all the depending on what settings you've got for cars. It'll fetch whether you've got an Octopus saving session active or not. It calculates all the energy rates, and then it works out the car plan if we've got one, and it stores that car plan. Works out today's costs so far. Fetches the solar forecast for PV, and it does the load filtering, fetching the previous historical load data and combining it, and it does the load today comparison. So this is all the stuff that's done in fetch sensor data here. Fetch inverter data is the thing that fetches the inverter information. So here, depending on how many inverters you've got, it goes around and creates one of these inverter classes for each one. And then it can also do the power curve calculations. It only does this once though, so you have to restart it if you want to do it again, because it's a little bit compute intensive. And then it sort of it accumulates all the inverters together to get the total. So it works out your total battery size and your maximum discharge and charge rates for all of them combined. So the way the planning works, you've got multiple inverters, it treats them as one single big inverter coupled together. If you want them as two separate ones, you'd have to run two instances of Predbat, but that wouldn't necessarily be advisable. And so this is where it prints out found so many inverters and the values that it's found. It also publishes the current charge windows information for where the inverter is set up, and then prints out this base thing. So that's the fetch inverter data. Then after that, it decides whether it's going to recompute the plan or not. If it doesn't recompute it, it's going to use the one that's computed previously, because this is the compute intensive thing. I mean, in my system, it only takes about 15 seconds or something, but some of them, depending on, especially if you're using Agile, it can take quite a few minutes. So it doesn't do this every time. It usually does it every other time, or if something's changed that forces it to do so. Publish rate and threshold is publishing the threshold for import and export rates. Then if we had to recompute the plan, because it can take so long, it refetches the inverter data again. Because in the meantime, the inverter may have changed, the battery percentage could have gone up or down, etc. Then it executes the plan. And so the execute plan is where you actually program the inverter registers based on the plan that you've calculated. Then obviously, depending on whether it did recompute the plan previously, if it hasn't recomputed it, then we'll see whether it is getting old enough. We do need to recompute it, and then it'll recompute the plan here. So actually, the thing to point out is the first compute only happens if the plan's completely invalid. The second one happens if it's past a certain time period, say more than 5 minutes old, for example. So here, normally the idea is you come in here, the plan's valid, you execute it immediately, so things happen on the 5-minute boundary. Then if you need to recompute, you spend the time recomputing it, and it takes longer to do that. So that might take a few minutes or something, but you do that afterwards, so that things happen in line with the current plan based on the 5 minutes. Then there's some updates, some information about iBoost, calculate those savings charts, the savings information that you need, store things into dashboard items, then update some information on the car and the holiday days left, and create some debug information if it's turned on, record the final status, turn active off, and save the current config. So just going to go back on that. I'm sorry, I forgot to say that if you did recompute the plan here, it would call execute a second time after it's, because if it took 3 or 4 minutes and the plan's recomputing, it's changed its mind, you want to do that now. So sometimes you will see the inverter controls twice in one iteration. That's because it's trying to do it fast to align with the 5 minutes, and then do it again if the plan's changed. And so that's kind of the main loop that it runs through every time. So that gives that basic information. The other thing I'll mention in this video just before I wrap up is obviously the config.py. It's got a whole bunch of constants in here, different settings which we saw are imported, and it's also got this config items table. This is all the things you can configure in Home Assistant, and it gives the name, which is essentially the entity name, except they're they've got some prefixes on to do with Predbat. So there'll be something like switch.predbat underscore, or there'll be Predbat dot something. So it gives you the type they are in Home Assistant. It gives the default value if there's no value set up, and the friendly name, which is the description. And then some of them, for example, input numbers have minimum, maximum values and steps. The unit, if there is one, to show, and an icon for that particular control. So you'll get a lot of these. Some of them also have also gate other features. So for example, the expert mode toggle is marked as the enable for some of these. So this says inverter SOC reset is only shown when an expert mode is turned on. So otherwise it's hidden and will always have the default value if it's hidden. So that's useful if you look through all of these. You can see what they mean. So that's what a lot of the code is here. Then the other thing that's in here is the inverter definitions for each inverter type and all the configuration options for that inverter, which is, this is used by the inverters PY class to decide how to control things. But some of these inverter options also propagate to predbat.py in terms of how it executes things. Because certain things have it, like if it doesn't support charge freeze, for example, then you don't want to calculate charge freezing. These config API overrides are for this, the Predbat API thing. I'll gloss over that for now because that's a little bit complicated. Some select mode controls as well in this config. So that's what you'll find in there. The other files we haven't talked about, apps.yaml, you know what that is already. That's the main configuration file that's read in when it starts. That's the static configuration. Download.py is the code that allows it to download versions from GitHub and install them directly. And then it just runs is once you've installed the version, because you've overwritten the files and because there's those triggers in the Hass code, it'll then quit and then restart it again and it'll start with a new version. So that's what the download code does. It's nothing particularly special. Future rate code is the thing that downloads Nord pool information and annotates it across agile rates. So that's just a calculation class, and the download code itself, it's got something that, and the downloads are also cached. So they're just stored in a local variable, so it doesn't do it on every iteration. And that's what that's about. HA, like I said, is the interface with Home Assistant. So this does WebSockets to communicate with Home Assistant, but it's also got some REST API calls for things like set state. Those things don't work with the WebSockets. And it also communicates, if enabled, with an SQL database where it will mirror data from Home Assistant to the local SQL database. I'm not really using that for anything yet. I'm just trialing it to see how efficient it is. But later on, I'm going to allow it so that all the charts can be generated from the database rather than from the Home Assistant one. And you could keep more state in this. So you could say maybe keep 90 days of Predbat data, but leave your rest of your Home Assistant on, say, the normal 10 days. So I think that might be useful. This is the API call that talks to Home Assistant for instant things like setting state and that sort of stuff. I'll cover that one in detail on another video. Then we have prediction.py. So this is the prediction class itself. And it's slightly more complicated because of these, the thread pool here. So there's various wrappers that control the thread pool. So I won't go too much into detail at the moment, but you'll see when the predictions created the class, it stores a bunch of things into global, and that's because it's being passed across to run through the multi-processing pool. Then you've got some run wrappers. But I think what you'll actually find in here is the main run prediction is the thing that calls and actually runs the prediction model and returns the results from the model. And that'll probably have its own video. We've got utils here, which is just for utilities like calculated percent from an SOC, moving intersecting windows. So this is where if you've got a charge and discharge at once, then the discharge wins and it kind of clips the charge around the discharge, getting charge rate curves and discharge rate curves, and finding the optimal charge rate for the time period. Web.py is the web interface itself. So this runs a web server and it serves up HTML. So you'll see a bunch of HTML in here, and it does the different tabs on it. The actual web application itself is something that's just imported here. So AIO HTTP has got its own web server in. So this is essentially just the code that creates the HTML and returns it. Then finally, we've also got a unit test here. And this I'm trying to build up. The coverage isn't brilliant at the moment, but it's got a whole load of unit tests that actually checks Predbat. And there's a bunch of tests here. So it runs execution tests, which is where it's trying to control an inverter. It runs the inverter, multi-inverter control testing. It runs tests of the models. Those are fairly comprehensive now. Window sorting test, optimized levels test is a sort of part of the optimizer testing. Compute metrics test is something here that works out, checks some of the metric values here and see if that's working. Run perf test just actually prints the performance of the Predbat prediction code, and the node pool test actually does the node pool interfacing and checks that that works. And so what you'll see here is if you want to set up the unit tests, I can show that one. So if I share the my other window here, and what you'll see is I've got a directory here where I put all the Predbat code in the Predbat debug directory, and then I've got a run all script, and the run all essentially copies like active code from the area, and then it runs the unit test code. And there is an apps.yaml in here, which is just a basic file that it will need to run it. So if I then source the run all, that will actually kick off my unit tests, and they all run, and if they fail, it will print a failure here. And so I've been trying to improve the coverage here over time. And there is, you can also run it with Python 3 coverage, and then you can review the coverage of the unit tests. And trying to add more so I can find bugs. So I think that's quite useful as it develops. And if anyone fancies contributing some unit tests of code, then that would be useful. This run normal test actually takes a while because it has to download agile rates from Octopus. So I may not put that in all the runs. I might have to change that because it's not something I change the code very often. So that's the way that one works. And then if I go back to the Visual Studio Code, let me see. Okay, so after that, there's the only other files in here. I think we talked about all the Python files. You'll see the Predbat config JSON file, which is essentially your current configuration. This is where it saves the information for the current config every time it runs, and it will reload it when it restarts, and then store those back into Home Assistant. You'll see the Predbat dashboard. This is the auto-generated dashboard, so you can include that in Home Assistant. You'll obviously see the Predbat log, which you're probably familiar with. It's just the log file of what's currently running. The only other thing here is that there's the Predbat save directory, and this has got some saves of if you save the current configuration. So this is one that I call that's just been date stamped. It's my current configuration, and previous is the previous configuration. So when you select save, it will save into here, and when you reload, you can load any one of these configs. The debug directory has got debug YAMLs. That's only when you've got debug mode turned on, it saves these. That might be useful for debugging stuff. You can obviously write those out. And then cache is essentially, it's got cached website information, which is only for Soulcast currently. So it saves it having to reload the Soulcast and running out of API downloads. And unzip, you only see from the first installation is where it unzipped the Predbat initially the first time you installed the add-on, so you can ignore that. And I think that's it really for what's in the directory. So on the next video, I'm going to go on and move on to the each of the steps in turn, actually talking in detail about how they work inside the code. If that was useful, but thanks for watching. Bye now.